Okay, differentials are another topic that have kind of been cut out of the curriculum, but I think they're important for some of the things moving forward. So I want you guys to think about the tangent line at the point C, f of c, very similar to that general form of the tangent line that we did in the previous video. The tangent line would be y minus f of c equals f prime, the value of the derivative at that point, times x minus c. Okay, so there's value in finding the tangent line and using the tangent line to approximate just the value of a function. Okay, so let's consider f of x equals 1 plus sine x at the point 0, 1. Okay, so first of all, if I want to find the equation of the tangent line, let's find the slope. So find the derivative. The derivative of 1 is 0. The derivative of sine x is cosine x. So if I want to find the value of the derivative at x equals 0, I would do cosine of 0, which is 1. Y minus 1 equals 1 times x minus 0. Just some quick rearranging, we can get that the equation of our tangent line is y equals x plus 1. And so on this graph, you can kind of see that the blue line is my tangent line, the red curve is the y equals sine of x plus 1. And you can see at x equals 1, that tangent line is pretty darn close. And in fact, we could look at x equals, let's go ahead and take a few seconds, or if you just trust me, we could find, using calculator, like what is 1 plus sine of negative 0.5. If I type that into my calculator, this is what I'm going to get. And so rather than make you guys do all of this, and then likewise doing 1 plus each of these. Okay, and so as we look at say at x equals negative 0.5, the tangent line isn't a terrible estimator. In fact, we see that the difference is approximately 0.21. To kind of envision that, that means this distance right here at x equals negative 0.5, this distance is 0.21, is 0.021. So it's almost like the value at that tangent line is pretty darn close, okay? And so, and in fact, as we look at the differences between each of these values, right at x equals 0, so right at that point C, at that point that we're talking about, the line is pretty darn close. And in fact, we can kind of think about what is this actual distance? So let's go ahead and turn the page. All right, and that difference is what we call, that distance between the line and the actual curve is what we call a differential, okay? So we know that that dy dx is equivalent to f prime of x. So we're going to start thinking about this little distance right here. That's our differential. That's our dy. It's like a microscopic distance between two y values, okay? Now, on the line, the slope of the line is delta y over delta x. Okay, so when we talk about delta y and delta x, those are talking about the slope of the tangent line. All right, dy is the difference between the tangent line and the actual function. Dx is equivalent to d. So dx is equal to delta x. So they both represent the distance, they're basically change in y over change in x, okay? All right, so as delta x and dx get smaller and smaller and smaller, like dx or dy and delta y get closer and closer and closer to each other, okay? So what's the big idea of this, okay? Here, the value of the function plus dy gets us the same y value here, okay? So if I want to find the y value of the function, it's related to the line and dy, okay? Well, let's consider the function f of x equals the square root of 1 plus x at the point x equals 3. If I plug in 3, I got the square root of 1 plus 3, which is the square root of 4. So f of 3 is equal to 2. And we can say f prime of x would be 1 over 2 times the square root of 1 plus x. If I look at that at x equals 3, well, so if I want, and so f prime of 3 would be, let's think of it this way. We can think of this as dy dx is equal to 1 over 2 square root of 1 plus x. So when we talk about differential form, we're essentially saying, what is dy? Because we want to look at what is the differential of just y. So dy would be 1 over 2 square root of 1 plus x dx. Because I would have to multiply both sides. Okay. So now, the whole point of using these is to find estimating values of a function. So let's think through, if I ask us to find f of 3.1. I know f of 3.1 is going to be close to 2. The question is, how close to 2 is it? Okay? So, if I ask what is delta x, which, by the way, is going to be the same thing as dx, well, essentially, we're looking from the change of this point, which is an easy point, so to this point. So my change in x is how much it changes from this point to whatever this new point is. So we're trying to figure out what is the y value at 3.1. So the x is changed by 0.1. And we can say f of 3.1 is equivalent, or approximately anyway, to the y value of our previous point plus dy, okay? So we say that if I go back to this picture. So let's, all right, so our best approximation of delta y, okay. Delta y our best approximation of delta y is dy, and we can figure out dy with respect from our differential form of our derivative. So our dy is going to be 1 over 2. My x is going to be 3. And my dx is going to be 0.1. So as we work this through, we can approximate that dy with 0.025. Again, this is just doing some arithmetic. So the actual, so then if I want to find what's our best approximation of 3.1, f of 3.1 is going to be the y we had before, 2, plus that delta y. So our best approximation is 2.025. Now, what is this, the square root of 1 plus 3.1? I type that into the calculator that you guys can't see, but it is sitting right next to me. I get 2.0248. So basic process is we use the differential form and the easy answer to estimate these different values. Let's look at another example. All right, so if I want to find f of 2.1, so what I'm going to do is I'm going to say, well, what is f of 2? Like, that's a really close value that's relatively easy to plug in. And my f of 2 would be 4 plus 6 is 10. All right, and my dx would be the difference between this 2 and the 2.1, so my dx is 0.1. And I can say that dy is equal to the derivative times dx. Okay, so now I'm making that estimate at x equals 2. My dy would be 2 times 2 plus 3 times 0.1. And that just tells me how different my y value at 2.1 is from my y value at 2. That's essentially what we're trying to do each time, is use the derivative to estimate the difference between my actual point that I'm trying to find and the easy point close to it. All right, so now a little bit of arithmetic here. This is 7 times 0.1 is 0.7. So our guess for f of 2.1 is going to be the 10 from f of 2 plus that change in y of 0.7. So our best guess is 10.7. If you plug in f of 2.1, you get 10.71. We're pretty darn close. All right, for this last one, in this case, I would use g of 3, and my dx would be negative 0.2 because I'm down by 0.2. If I plug in 3, I've got the square root of 25 minus 9, which is 16, which is 4. Okay, and then my derivative, I would have 1 over 2 times the square root of 25 minus x squared, chain rule time would give me times 2x times dx. Fill in everything I know. Work that out. And I'm finding, when I type this into my calculator, I'm getting 0.15. Okay, so my g of 2.8 would be 4 plus 0.15, 4.15.